I'm Krish Mehta, and today I'll be talking about the isotope of plutonium, plutonium-238. An isotope is another version of an element, which obtains a different number of neutrons than the rest. I picked the man-made isotope plutonium-238, where the 238 indicates the atomic mass of the isotope. Interestingly, this isotope is the most rare plutonium isotope, with an abundance of 1.81%. It was named after the dwarf planet Pluto. Plutonium-238 was discovered in 1941 by three scientists, Glenn Seaborg, Joseph Kennedy, and Arthur Wall. Seaborg bombarded the isotope uranium-238 with the deuterium's nucleus, deuteron, where beta decay occurred due to too many protons and another neutron escaped, forming the isotope neptunium-238. The neptunium-238 then underwent beta decay, being converted into the isotope plutonium-238. The larger the gap between the number of protons and neutrons, the greater the instability of the atom, the more the ionizing radiation that is emitted, and the more radioactive the element will be. Since the number of protons in plutonium-238 is 94 and the number of neutrons is 144, the gap is very large, thus making the element very radioactive. The half-life of plutonium is very long, roughly 87.7 years. Plutonium-238, when decaying, releases alpha particles, implicating that it undergoes alpha decay. An alpha particle's nucleus is identical to that of a helium nucleus. Plutonium-238 naturally decays into uranium-234. This is logical because when plutonium-238 releases an alpha particle, its proton count, which is 94, goes down by 2, becoming 92, and the element with atomic number 92 is only uranium. The atomic mass, which is 238 of plutonium, goes down by 4, becoming 234, finally forming uranium-234. Throughout plutonium's radioactive decay process, it generates and releases extreme amounts of heat. This makes plutonium useful in providing heat where it may be difficult to generate heat, such as in space. Its heat-generating capabilities are put at use in generating electricity from the heat, and using it to power different machines in spacecrafts, rovers, satellites, etc. It is currently in use on the Curiosity rover and the New Horizons spacecraft, both by NASA. Its long 87.7-year half-life, high power density, meaning it can generate substantial amounts of heat with a little quantity, low neutron, beta, and gamma radiation emissions, and many more factors make plutonium-238 the best choice of isotope for space missions. Plutonium-238 has absolutely no positive impacts on the environment or our body. The only benefit that plutonium is widely used to provide is the steady generation of heat to convert into electricity. Plutonium is one of the most dangerous elements on the periodic table. It can have many negative impacts on the human body if the person is directly exposed to the plutonium. If you hold plutonium in your hands, by the time your hands are reasonably warm, you will have died from extreme radiation exposure. As well, if the alpha particles during decay are inhaled, they will get lodged or stuck in the lungs, killing the lung cells and causing scarring or other potential diseases or cancer. Plutonium can also negatively impact the environment in many ways. Firstly, there can be a nuclear accident when the plutonium is exposed to the atmosphere and releases radiation everywhere, killing all life in its way, or due to improper disposal of the radioactive waste. As well, if plutonium is dropped on soil, the element will slowly work its way through the soil, getting into and harming groundwater, which is fresh water, eventually harming wildlife and humans. These were some of the things I learned about the plutonium isotope, plutonium-238.